So today I did want to go ahead and finish looking at these limits intuitively. This is the final filled out version of the flowchart that we're going to be looking at. And in this flowchart, you can see the different ways that we can look at limits. So we know that we always are going to look at them by a substitution first, and that's the first thing you always want to try to do. When you get a real number or when you get a number over zero, those are going to be the easy ones because those are going to be the ones where you can stop. That is your answer. The cases that we're going to continue with is looking at these indeterminate cases. And the indeterminate cases that we have are going to be like 0 over 0. We have infinity over infinity. And then we have some other cases. We already looked at algebra, so we know that different algebra skills we have. We can factor and cancel. We can rationalize or do other algebra. The main goal is that for all those, technically, we should have some sort of canceling happening so that we can go back and do direct substitution. Yesterday, we talked about FEPL and what matters most, which is a way to determine like what's the most important part of the function or what's increasing the fastest, where's the function going and things like that. I did go ahead and add up here just so you know it is a thing that exists, and that is called L'Hopital's rule. Yes, that is French for the hospital, but that was also a mathematician's last name. We won't cover L'Hopital's rule until unit 2 or 3, but I did just want to kind of let you know that it does exist, and we will be coming back to limits later this semester. And then the last kind of blank I have is infinity minus infinity. So these are going to be all your limits that basically aren't written as fractions. Some other ones that might be related to infinity minus infinity is something like an undefined expression minus another undefined expression. So kind of all these weird other cases we can have in math that don't really mean anything to us. And for those, we're basically going to do just some algebra. Whether it's finding a common denominator, rewriting it, and things like that. But that's basically how we're going to be looking at limits in this class. To finish out the notes, the first example I wanted to give is an example like this that asks, what should you do when you have two separate rational expressions? So I have the problem, the limit as x goes to 0. Of x plus 1 over 0 minus 3 over x squared plus 3x. So we know that the first thing you want to do always when you have a limit is to do your direct substitution. So plugging in 0 into that first fraction, I'm going to end up with 0 plus 1 over 0, which is basically going to give me 1 over 0 for that first part. And so with my direct substitution, I'm going to write it at the top. I have 1 minus 0 minus, plugging in 0 again, I have 3 over 0. And to be clear with this, like we know that 1 over 0 is undefined. Well, 3 over 0 is also undefined. And for this limit, your answer is not going to be undefined or does not exist. Because we need to think about what it means when we say undefined. Like undefined literally means like we don't know what it means. There's no meaning to it being undefined. So you can't have undefined minus undefined. That means nothing in mathematics. So what should you do when you have two separate fractions and they both end up something weird like this is you would want to simplify that by finding a common denominator. The goal is after you find that common denominator, hopefully something cancels out and you're able to then do direct substitution. For this one, we can check and that does work. So I have the limit as x goes to 0. The second fraction, when you factor that denominator, it becomes x times x plus 3. So we can see that the common denominator is just going to be x times x plus 3. So that first fraction, it just had an x in the denominator, so we need to multiply the top and the bottom by x plus 3. That second fraction had the common denominator already, so we didn't need to do anything. Again, you can plug in 0, but we still get 0 over 0, so we would want to simplify this a little bit more. So I'm going to go ahead and use my algebra skills to FOIL this together. Again, never waste your time factorialing together the denominator, because again, the ultimate goal should be that something eventually cancels out. So I can see the plus 3 and minus 3 cancel out. So with what's left over, the denominator is fine leaving it as is. The numerator you can factor out an x, and it can be written as x times x plus 4. Now these cancel. We no longer have undefined over undefined. We no longer have 0 over 0. We now have something that makes sense, and the limit for this is 4/3. Some conceptual things I want to remind you of. Remember that when we cancel, that is technically a hole. So one thing we know about this graph, because it does have a limit that exists, is there is a hole in the graph, and that hole is at the x coordinate of 0 and the y coordinate of 4/3. Questions or concerns about that problem? All right, let's look at the next set. So for this one, I have 2 questions, same graph. One is going towards positive infinity, and another one is going towards the negative infinity. So when I'm looking at this one, I have the limit as x goes to infinity of 2x minus 8 all over the square root of x squared minus 5x plus 4. So let's think about this one. If you had this problem, you're looking at it on homework, you're looking at it on your quiz, test, AP exam. Let's talk about that first one going to positive infinity. What might be some things you think about or do first? If someone wants to unmute their mic and take a stab at that.
Plug in. Factor.
Or I guess we're all going to talk at the same time. Go ahead, Anna, I think I heard your voice.
I was gonna say FEPL because it's approaching infinity.
Okay, so it is FEPL. So I'm looking at FEPL. Both of these are kind of polynomials. I do also notice I have a lot more terms. So I guess you could argue like FEPL works, but these are both in some ways polynomials or powers. So I might ask myself what matters most first as well. Because we know that when we are going, you're correct, to infinity, we can often simplify that problem. For example, if we're going towards infinity in that numerator, what's really going to matter most in that numerator? What will be more important at infinity, a 2x or taking away 8? The 2x by far, that is much larger at infinity. And then the numerator, in the denominator, what's going to matter most?
Square root of x squared.
The square root of x squared. And Seth, I'm glad you said the square root of x squared, because that x squared is inside the square root. So the end behavior model for this problem can be written as the limit as x goes to infinity of 2x over the square root of x. And remember when I say the end behavior model, what this means is at infinity, this simplified function is going to look the same way as the other one. I am also going to go ahead and write it since it's the same function underneath it, and we're going towards negative infinity. I'm also going to, for that second example, go ahead and write out the simplified example. And so now I want to kind of think about what's happening. In math, when I see the square root of x squared, what do I know that the square root of x squared is? X, like, and we know that we've been doing that forever. I don't want to say we've been lied to, but we've been kind of skipping over some processes when we say what is the square root of x squared. So I'm going to go off to the side on the right hand side. If you have the equation, say x squared is equal to 9, and I told you to solve that equation, what do you know x is going to be equal to for that equation?
Plus or minus
3.
Plus or minus 3. And you've been told that forever, like, you know, that's just how taking the square root works. And so we know that when you take the square root of both sides, you end up with like the square root of x squared is equal to the square root of 9. And where that plus or minus is actually coming from, so you know the square root of 9 is 3. and this is where even myself included, kind of teachers just skip over. The square root of x squared is actually defined mathematically as the absolute value of x. Well, what does the absolute value do? The absolute value, things can be positive or negative. So when I say the absolute value of x is 3, that's where we're getting the plus or minus from. And so for the sake of calculus, it will help you out if, especially for limits, if you see the square root of x squared, we're going to think of that as being the absolute value of x. Meaning we have to consider it from, it could have been originally a positive number, or it could have been originally a negative number. So think of that absolute value of x for this problem. So I'm going to rewrite the limit as as x goes to infinity of 2x over the absolute value of x. And so this is where we need to go ahead and make a decision. So when I'm looking at 2x over the absolute value of x, this is where the intuitive part comes into play, because technically we can't cancel those x's. One is inside of the absolute value, the other one is not. But we can kind of imagine if that absolute value was not there, they could cancel out. But when they cancel out, it could be a positive one, or it could have been a negative one, depending on what that x value is. So here's my thinking for this one. I know the answer is 2. Like, if I could cancel those out, there is going to be a 2 somewhere in my answer. And that's the big if I could have canceled those out, because they are the same value. What I do need to determine, though, is the sign. So if I'm coming in for that first one, I'm coming in as x is going towards positive infinity. So if we're on the positive side of x, well, the absolute value is always positive. The x values in the numerator would also be positive if I'm coming from towards positive infinity. Well, a positive over a positive means that those could cancel out and become positive 1. So my final answer would be positive 2. That changes if I'm going towards negative infinity, because if I'm going towards negative infinity, the absolute value itself is still positive. But this numerator, if x's are going towards negative numbers, then 2 times x is actually going to end up being a negative number. So when those x's cancel, they're actually going to become not a positive 1, but a negative 1. So we still have the 2, but the answer for this one is going to be negative 2. So we still had to consider what those x values were. And again, I was just thinking, like, we'll only be doing this really when we're going towards a positive or negative infinity. So we see that from one direction it is at positive 2, from the other direction it is approaching negative 2. Questions or concerns about that problem? All right, I think I have 2 more. Chose this one just because it's another one that we can do some stuff with. It's not really an intuitive one, but looking at that one, I chose the same rational expression. And I want you to find the limit as x goes to 4 from the right. Whenever you're coming in at a number from the left or the right, you can still do direct substitution. Like, you'll get to the same answer as long as you do proper algebra and things like that. So the first thing you do when you see this problem is, of course, direct substitution. Well, 2 times 4 minus 8 is 0. And then the denominator, 4 squared, so 16 minus 20 plus 4, 0, which is probably what you expected I would give you. So we know that when we get 0 over 0, that is an example where we need to keep going. So if you were looking at this problem and had to do it on your own, what might be something you try to do? Any suggestions?
Rationalize.
You could rationalize. And so I'm going to say, yes, rationalize would definitely work. You would get to the answer. You could also go ahead and factor and kind of simplify now. So I do want to be clear. One option, you could rationalize And then after you rationalize, you're going to factor and cancel. Option 2, which is the one I'm going to do because it's kind of a shortcut, is you can just go ahead and factor and cancel to begin with. And the reason why I know I can factor and cancel to begin with is in that denominator, there's no number added or subtracted to that square root. So yes, you could rationalize it. I'm going to go ahead and simplify it to begin with. And so to simplify it, I see that numerator, I can factor out a 2, and I get x minus 4. That denominator, I have x and x, and it's going to be a -4 and a -1. And so looking at this, we want something to cancel, but we do need to kind of be careful when we're canceling. So x minus 4 itself can't just cancel out completely. What's technically the exponent on the x minus 4 in the numerator?
1/2.
1/2.
In the numerator. I mean, I
One.
guess that's going to be the answer. So let me jump in. So right now it's
Oh,
1.
1.
I know many of you are seeing where this is going. In the denominator, this is technically x minus 4 to what power?
1/2.
1/2. Could also say x to the minus 1 is also the 1/2. So we know properties of exponents. If we have the same base and we are dividing, we can subtract the exponents. So this problem ends up simplifying. The 2 can't be touched. And x minus 4 divided by the square root of x minus 4, 1 minus 1/2 is going to give you 1/2 in the numerator. And then you still have an x minus 1 left over in the denominator, which you couldn't do anything with. At this point, can you go ahead and substitute 4 into that equation? Yes, you can. Plugging it in,
Yes.
you end up with 2 times 0 over the square root of 3. 0 over number is just 0. So again, we've taken it to a problem we couldn't do because we had 0 over 0 to a problem that we could do by basically simplifying it. But you could have rationalized it as well, but you still would have ended up factoring and canceling something.
Does it change anything if you're approaching 4 from the left?
Can you say it one more time?
Does it change anything if you are approaching 4 from the left? Like, does it do anything different?
It doesn't. I had to write the problem this way because the portion of the graph, I'm going to draw it for you. It looks like this. It's like, it's a little bit steeper at 0, but basically it just doesn't exist on the left-hand side of 4. So mathematically, it wouldn't have made sense for me to write a problem that was just as x goes to 4. And that was just like a technicality because I knew what the domain of this function was already, so I just wanted to write a problem that made sense mathematically. But to kind of go along with your question, if this graph was, coming to both sides of 4, then no, it would not change anything if I just had 4 there or if I had coming at 4 from the left. But for this particular graph, it just doesn't exist on the left-hand side of 4. Any other questions? All right, last one. Want to choose one that looks a little bit fun. So this is an example with factorial. And I will say some of you can probably look at this and use FEPL and figure out which side of this problem is going to have the bigger infinity and know whether it's going to go to 0 or whether maybe they're equal and go to a number. But I do want to just show you how we can simplify these problems, because I think simplifying it does make it a whole lot easier. So some things I just wanted to review in general, like we know we have FEPL. So like factorials have the largest growth, then exponentials, then powers, and then logs. And then we also know things like when the biggest infinity is on the bottom, then that problem is going to go towards 0. When the bigger infinity is up top, then that problem is going to go towards an infinity with a limit that is D and E. So I know if you're looking at this one, some of you can look at this one and tell which one's going to be the larger one. But I do want to kind of show you how we can simplifying it, just because I think, well, one, you should know how to simplify factorials and exponents. And two, I do think it makes the answer a little bit more obvious. So let's simplify the factorials first. So I'm just going to go ahead and write out my statement here. So let's review. When I say something like 4 factorial, what does that mean?
4 times 3 times 2 times 1.
4 times 3 times 2 times 1. So 4 times 3 times 2 times 1. We know that. So if I change that, so looking in that numerator, it says we have x plus 1 factorial. So if I'm multiplying that out, the first number we start multiplying with is x plus 1. What will we multiply after x plus 1? Or what will be the next number smaller than x plus 1?
X.
X, right? So if I have x plus 1, the one smaller would be x. Just make sure we're getting the pattern. What will be the next number smaller than x?
X minus 1.
X minus 1. And we could continue that, like x minus 1, x minus 2, but we know we'll eventually get down to 2 times 1. But we can actually simplify that a little bit more and condense it. So I know I have this x plus 1 here. When I was starting with x and multiplying all the way down to 1, I know that that's the same thing as writing just x factorial. So one way that I can write x plus 1 factorial is that the same thing as saying x plus 1 times x all the way down to 1. Well, what is x all the way down to 1? It's just x factorial. Why that's useful, x plus 1 factorial in the numerator can be broken down to look like this. And then we have an x factorial in the denominator, so we can start seeing how some things would cancel out. Questions on how I simplify the factorial? All right, let's review some exponents. If I have 5 to the 2nd power times 5 to the 4th power, what can we write that as instead?
5 to the 6th.
5 to the 6th power, so we know, not a trick question, we just add the exponents. We can also do that in reverse. So for example, in that denominator, I see we have a 5 to the x plus 1. What's another way I can write 5 to the x plus 1 using those properties of exponents?
5 to the x times 5.
Correct, 5 to the x times 5. Could put the first there, but times 5. And then there we do now can see lots of things cancel out. So I have the factorials cancel out, don't even have to worry about them. The 5 to the x's cancel out, don't have to worry about them. So my simplified limit, should have left some more space, but I have the limit as x goes to infinity. In the numerator, I have x plus 1, and the denominator, I just have a 5. So this is the simplified limit. So if x is going towards infinity, I know that means x in the numerator is going towards infinity. The denominator is just a 5, so it's not changing. So if I have infinity divided by 5, what are we going to say that limit is going towards?
Infinity.
Infinity, and if the limit's going towards infinity, what do we say the answer to the limit is?
Does not exist.
Does not exist. If that fraction had been flipped, so 5 over the x plus 1, then the limit would have been going towards 0. And where many of you could probably figure out was going towards infinity anyways, is in that original problem, all of those are factors. Well, if I'm kind of using FEPL, the biggest parts of those are the 2 factorials. And x plus 1 factorial is actually way, way bigger than x factorial, since you're multiplying by one whole extra number. So you can probably assume without doing all that work that it is top heavy, so going to be D and E. But I did want to do that problem just to show you some different ways that we could simplify factorials. Not that we see too many in calculus in unit 1, but we will start seeing more and more in BC as the year goes on. Any questions on that problem or anything else I can go back and clarify? All right, so that puts us, that's the end of my notes today. So it's almost 1 o'clock. So there are about 10 minutes left of class. The homework assignments you have so far are homework 1, 2, and 3. And those are basically going to be the topics that are on your quiz on Thursday. Tomorrow is just a work day. I am going to ask for you just to log in right at the beginning of class, just so I can give you the details about your quiz, like the number of questions, and just answer any general questions or concerns you have. So at this point, if you're good to go, like you can go ahead and log out and enjoy the rest of your Tuesday. If you want to hang back and ask questions, I won't end this meeting until class ends, and you're more than welcome to hang back and ask questions on things like homework problems, or if you want to go back and ask questions on notes, that's fine as well. But if you're good to go, then see ya. If not, then you can just hang back, or at least hang back and see if anyone asks a question that you might have.
Thank you, Mr. Brown. See you
ya.
tomorrow.
Will wanted me to tell you that I wouldn't let him join the meeting.
Okay.
No, I got
Oh.
like 20
Oh,
minutes
he's
late.
back in. Oh,
Yeah.
Will, if you want to go back and see the first part of the notes, they'll be posted by 2 p.m. today.
Okay, thank you.
And to see them, you'll just go to like the Meet Here channel and then look at the tab that says class recordings.
Thank you.
I got a question. So like